That bounced a little more than I thought it would.
Ow! I'm studying! I promise!
Collisions are actually pretty simple. It's just two objects that are touching or overlapping a little bit because of physics frames. And then after that, they've collided with some force and they bounce off of each other in some way. This particular tutorial is going to be a three-part tutorial. This one's going to cover circles, another one's going to cover lines, and then the last one will be complex objects where they're combined together. Determining if something's colliding really is pretty intuitive, just like that one up there. It's just two objects hitting another one, they overlap a little bit, you can kind of work out the physics. When you have something a little more complicated like that one, it's a little more difficult to figure out where those particular bounces are supposed to go. So to work through it, we can do something a little simpler and try to apply a collision force between the two objects, which is that yellow line there, and it's a lot easier to work with and we can determine where things are going from there. The math for actually processing a collision is pretty simple stuff. We just have a couple of vectors to work with and a dot product. After that, it's a multiplication and a little bit of addition, and everything kind of works out. You also have to worry about things that have a little bit of rubberiness to it. So a ball might be a little more bouncy than another ball, or a steel ball will hit the ground, not bounce a lot, but a rubber one will. So we have a little bit of that processing along with it. It's a very simple floating point value, and we can add those together, we get the same effect. So even though that collisions is an easy math, we have a little bit of a problem with overlap. So that overlap, like this one here, we have one circle in the middle colliding with two circles on the outside. When you move the middle ball outside of the two outside ones, it automatically will go the right direction. But if you have one like this, where the overlap is actually majorly to one line, and you correct for it and it pushed itself through another line, that's going to be kind of a bit of a problem. Another issue might come up where you have overlap like this, where it's going over a circle, over a line, and colliding with a line it should never have collided with in the first place. So in these types of situations, we have a bit of a problem, and we don't know which one's actually the correct one. The bounce is going to be really weird because collisions that shouldn't have happened are. So there'll be a little bit of advice in this video of how to correct for that as well. So working with circles and spheres seems kind of basic. You're probably going to have mostly complex objects like a ship or an asteroid or some other building in weird shape. You're not going to have too many circles. But if you have a complex shape like that, and you have all the collisions that are possible in the game, you kind of want to eliminate all that in math before you get to it, because that's a lot of processing. So in this case, you have this particular diagram, you put circles around those complicated objects, and if things aren't within the circle, we don't have to check for collisions anymore. So we end up saving a lot of CPU time, we can have a lot of spikes in our physics engine, and everything becomes more efficient and easier to process, which everybody likes. So detecting collisions between circles or spheres is pretty simple. All you have to do is draw a vector between the two center points, determine what the length of that vector is, and if it is less than or equal to the sum of the radii of the circles or spheres, then it's colliding. Something to note though is that a lot of engines will have a possibility of having a square version of the length. What that means is they have not done the square root, which means it's a lot faster to retrieve. So to work with that, you just take the radii and you times it by itself. You now have a square. It's quicker math. You end up with a lot more performance in the long run. So using the vector that we had in the detection portion, we have a start position and an external object that we're working with. So we can take the normalized version of that particular vector, so it's pointing at the external object, and then we have the velocity of the start object. We will normalize that as well, and then we dot product them together. So that gives us a percentage of the velocity as moving away or towards that other object. And you can reverse that back and forth, depending on how you want the actual start object and external object to be. With the percentage of velocity we have, we know now if it's moving towards the object or away. So it's going to be a value between -1 and 1. Negative numbers being moving away, positive numbers moving toward the other object. So to give a visual representation of what I was rambling about, if you take this particular image, I have the vector between the two objects pointed the wrong direction. when I take the dot product, it's pointing the wrong direction. So to reverse that particular vector between the two objects, I can just multiply by -1, and that kind of flips it back and forth however we want. So when we do that, we get this image, which is now pointing the correct direction. So instead of it moving away by math, even though it's actually moving toward, we now have it pointing the right direction. We get the proper dot product value, and now we can work with the actual values overall. So when we flip it back and forth, we can actually have the external object and start object switch, and then we can do the dot product, and now we get a consistent value of the velocity towards the other object. So when we work with that, we get this image, and now we can add the two items together. We get the vector or velocity toward each other, and we can calculate the force of the actual collision. So when we start calculating the actual force of the collision, it's really important to remember that there's a mass involved and there's also a velocity involved. But first is we have to make sure that the objects are actually going to collide and moving toward each other. So to do that, we take those items that we had before. So we have a scalar product, which is the percentage of velocity towards the other object. We times that by the velocity of that particular object and work with the other one, do the same thing, and we add the two together. So if the overall value is positive, then they are moving toward each other. If the overall sum together is not moving together, then they are moving apart, and we don't do any more calculations. So this kind of saves us a lot of calculations because there's no collision, they're moving apart from each other. The other part is that once we actually know that they are moving toward each other, we need to find the actual force of the overall collision. So that's where the mass comes in of the object. If everything's the same mass, it's easy, we don't have to worry about that. But we have different mass objects, we have to calculate it in, it's really important. So what we do is we take the velocity of an object, times it by the mass, and then times it by the percentage of the velocity that's moving toward the other object. We do it for both of those, and then add them together. Overall sum equals the actual collision force that we're going to apply. So now that we have the force calculated, we know that objects themselves aren't perfectly bouncy. So we're going to have an object that has a value between 0 and 1 for how bouncy it is. A 1 is a perfect bounce. So if you drop an object from a particular height, it hits the ground, it bounces back up, it goes back to exactly the same height you had before because it absorbed no energy. It was a perfect bounce. So we have that in consideration. We add the two pieces together so each object has a bouncy value. You add it together and then you multiply it by the force because you have an equal and opposite reaction. Something to consider is that if that combination is below 1, it's not going to bounce off the object. So you have a perfect bounce versus a 0 bounce, then it just hits the object and sticks to it. It also means you can have something below 1, which is going to be a problem, so minimize it to 1. Also, the object should have no more than 2 as overall. Now that we've done this math and this math, all we have left is to make sure that we have all the forces in one particular place. We've applied the bounce factor to each of those forces, and we put them all together. So when we apply the collision force, we have to make sure it's coming from the external object and aiming into the actual object we're applying the force to. So we can flip that back and forth to -1 math, and we get a force that we want to apply. Each object's going to have a list of forces that are applied to each frame, and at the end of the frame, they're all calculated together. You get an overall force applied to an object. The engine kind of takes care of that. So now that we've actually calculated the forces we have to apply, there's one more problem we have to take care of, the overlap issue. We have two circles actually overlapping each other. It's really rare that they're actually going to be just touching, so we have to do this on every single frame. What we can do is we take the radii that we had summed together in the detection portion, and actually the length of the two objects that we used for are they touching, and we take those in a difference and we determine the actual gap between those two, which is the overlap of the objects. So if we just randomly divide it by 2 and move the objects away from each other along that vector, then they basically go from overlap to perfectly just touching. The issue with that is if you have multiple objects stacked in a row, you have an object move away from each other, and now it's moving into another object. If now the overlap is moved to another object, the next frame it moves back and forth, back and forth. What I found is a really good solution for that, instead of dividing by 2, to divide by 4 or 8, and actually have it partially move away from each other. So if you have a lot of different overall overlaps, they kind of force themselves apart from each other, and they kind of self-correct over time. So after 4 or 5 frames, now they're all perfectly stacked and just touching, as opposed to being overlapped and bouncing back and forth endlessly. So over the course of a few frames, the overall user is not going to notice it, not really a big problem. If it does, you have maybe like 8 or 9 objects all stacked on top of each other, you might have an issue. You might have to kind of play with that value in order to get something about right. So with the simplistic physics that we're working with, we also have some really kind of annoying problems that come along with it. Simple math equals, well, simple problems, but we can kind of work through them and kind of figure out the problems and kind of work around them. So one of the main ones is that if you have an object move through another object, if it goes halfway overlap, it's now passing past the object and moving out. So you kind of have a problem where things are going to teleport through another object. But that distance of allowed overlap is now half of the radius of one of the circles, whichever the smallest circle is. Another option is that if you have a stack of objects, like a circle on top of each other, and you apply gravity to them. Now the mass of the top object might be enough to actually force the bottom ball through a wall, because all these things, collisions on top of it, are now pushing enough force to make it move far enough to get through it. Or the collision overlap is now enough to make all the balls kind of start pushing through each other and eventually pass through the wall on the bottom. So another known issue with this is that if you have a large difference in masses, the forces can be kind of wild and crazy a bit. So you have like an object that's 10,000 masses larger than a particle that you have, so it hits it, and now that particle goes flinging off at some unrealistic speeds, and you kind of have to deal with that. So something to work with that is to fix it by putting a cap limit on a collision force, or an end velocity or momentum of an object. You can kind of cap it off so it doesn't become unrealistic or ridiculous. Also with that, if you have an object moving really, really fast, it's more likely to pass through another object. If it's a small radius going really fast through an object, it might be moving each frame more than half of its own diameter. So you have a small particle, it hits a wall, but because of the radius of that particular object is so small, it moves past its own half radius, and now it's never had a chance to collide with the object, and it just passes straight through it. So now that you know well more about circle collisions than you ever thought would be important, you probably find that they're pretty useful, but they seem rather limited in their actual implementation in a game. You'll probably find that if you have a line, you probably need a circle at the end. If you have complex objects, they're a line and a circle. If you're dealing with 3 dimensions, it's a sphere and a plane. So actually it becomes very useful overall. You're going to be using a lot of this stuff. It's also the easiest one to understand. So if you still have a little trouble with some of the details, leave some comments below. I'll be more than happy to help you out. Make sure you hit like and subscribe if this is useful for you, and thanks.
Ow! I'm studying! I promise!
To do that, you can have some basic idea of how we're going to work with this and then forget what we're going to say. But that's really kind of how it works out for me. Just a line in a sphere. You're going to have complex objects like a shape or an asteroid, maybe. Shape or an asteroid, for example. It's basic things, and there goes the phone.